You all for joining. My name is Michael Molina. I'm the Workforce Development Coordinator for SPTC and Librarian for Oklahoma Transportation Library. I think you're in for a real treat this afternoon. We have a couple of good distinguished guests speaking today for our workshop. I'll do a little bit of housekeeping rules and do a brief introduction, and then I'll turn it over to our speakers. But first of all, the webinar is going to run for about 2.5 hours. If you attend the full webinar, you're going to get 2 professional development hours. During the presentation, make sure your microphone and your screen is both muted and hidden out of respect for our speakers. We want the focus to be on them. If you have a question, please feel free to type it into the chat or raise your hand, and we can unmute you during the Q&A portion of this workshop, which will be at the end. We'll also send out a survey afterwards, and you can let us know how we did and suggest future topics for future webinars. So without further ado, I'd like to introduce our speakers. First, we have Dr. Imad Abdullah, Associate Professor in the Department of Civil Engineering at the University of Texas, El Paso. And secondly, we have Sandeep Reddy, PhD candidate, also in civil engineering at University of Texas, El Paso. And they're going to be covering the topic Advanced Asphalt Mix Design, coming full circle by adding frictional performance. So I'd like to turn it over to our speakers. Thank you so much.
Thanks, Michael. I'll go ahead and start the presentation. I guess, Sandeep, if you don't mind sharing.
Can you see the screen, Dr. Imad?
It's not in presentation mode. I think I have to. There we go. So, good afternoon, everyone. Thank you for having us here to present at the workshop. I'd like to thank the Southern Plains Transportation Center. It's a pleasure. I'm glad you allowed us to choose this topic to present. We started this research about 3 to 4 years ago. We started from a small case study and it manifested to several projects put together. So today we're going to be talking a little bit about asphalt and aggregates and the frictional performance of both. And I'm very lucky to have a PhD candidate. He defended, he's ready to graduate, Dr. Reddy. So I thought what better for not to have him present the study. Yes. So I'm going to have him take a presentation, and I think if you guys have any questions, if you don't mind holding till the end, we will be glad to answer as best as possible. Like I said, this research started with a small project, and over the years it got to include many studies. So yeah, we might we had 2.5 hours to put everything together, so there might be some things that we present a little bit not as detailed as other stuff. So if you have questions, we would love to answer. We're very excited in working on this project, and I will turn it over to Sandeep to start the presentation.
Okay, thank you, Dr. Abdullah, for the introduction. Good afternoon, everyone. As Dr. Abdullah mentioned, my name is Sandeep Reddy. I'm a PhD candidate in the Department of Civil Engineering here at the University of Texas, El Paso. So in this workshop series, the topic is Advancing Asphalt Mix Design, coming full circle by adding frictional performance. So what we are going to have in this presentation is, so this is kind of outline that we have for this today's workshop. So first I'm gonna give a background of the study, in which I'm gonna talk about talk about where this workshop fits in the field of asphalt pavements. And then at second I'm gonna talk about the asphalt skid resistance, in which I'm gonna talk about the factors that influence the skid resistance and the methods that we use to evaluate pavement skid resistance in the field. And I'm also going to talk about the method that we follow in our laboratory to evaluate the asphalt mixture frictional performance. Then at third, the main important thing is the significance of the study, in which I'm going to talk about how we can incorporate skid resistance or frictional resistance during the asphalt mix design stage. and more specifically the gaps that we identified and how we try to address those research gaps. At fourth, I'm gonna talk about the results, in which I'm gonna elaborate more on the asphalt mixture frictional performance. And then at fifth, I'm gonna talk about the alternative aggregate friction test results. And then at six, I'm gonna present the conclusions that we can have as part of these study results. And then at last, the acknowledgements. Okay, before getting started with today's presentation, I would like to present this disclaimer, and I'll request all the attendees to read this disclaimer before getting started with the background of the study. So I'll stop on this slide for approximately like 1 minute, and I request everybody to read this disclaimer. Okay, all right, let's get started with the presentation. So, as we know, the topic of today's presentation is related to transportation engineering, and we know in the field of transportation engineering we have different categories. Among these categories, our today's topic fits into the category of pavement materials. Then at the right hand side in this slide, I am presenting the topics that were covered as part of the SPTC webinars, short courses at workshop. So we can see here in this box the different kinds of topics that were already covered as part of these SPTC webinars, workshops, and short courses. So what's today topic is about the asphalt mixture frictional performance. So we are gonna add this topic into the SPTC topics list. So if we look at the types of pavement, as we know, flexible and rigid are two broad classes of pavement types. These names were given based on the way that they behave when the loads are applied on these structures. So basically, in the flexible pavement, we have asphalt as top layer, whereas in rigid pavement, we have cement concrete as top layer. Since the asphalt layer in flexible pavement is a viscoelastic layer, so the entire pavement structure behaves in a flexible way, whereas in the rigid pavement, the top layer, which is a concrete layer, which is very strong in terms of its compressive strength and which also has high modulus of elasticity. So for those reasons, the entire pavement structure behaves in a rigid way. However, when it comes to the pavement type selection, most of the times it goes to the flexible pavement rather than the rigid pavement. So there are two major factors that causes this selection process, and during the selection process it goes to flexible pavement. Those are initial construction cost and ease in maintenance. So for the flexible payments, the initial construction cost is very low when compared with the rigid payment, and the ease in maintenance of flexible payment is very easy in comparison to the rigid payments. So if I take some maintenance example, so in flexible payment, if the top layer has some cracks, so it is easy to replace that just by doing the milling process. We can add a new layer. Whereas when it comes to any cracks or any failures on the rigid pavements, removing the top cement concrete layer is kind of hard because it's very brittle and it is very strong. So it takes ease in maintenance process very cumbersome. If you so the today's topic is more specifically on flexible payment, and this workshop scope is out of the rigid payments. So if you look at the advancements that were occurred in the recent decades, so there were numerous advancements. I tried to present here in this box the advancements that were occurred in the recent decades. related to flexible pavement. I would like to take few examples related to each layer. So if we start with the subgrade, the advancement that were occurred in the recent decade would be like soil treatment, which are like lime stabilization, cement stabilization, and something like improving the compaction process by using different compaction methods, something like that. If we look at the advancement that were related to base and sub-base layers, I would like to say based on the ones that are highlighted here, uh, few would be like crushed rock bases, stabilized bases, recycled bases, and granular sub-base and base layers. So these are like kind of advancements that were occurred in the past decade related to base and sub-base layers. More specifically, the advancements are more for the asphalt layer because for the two reasons, because this is on the top. Since it is on the top, it is subjected and it is directly in contact with the heavy loads. So basically the top layer takes high stresses in comparison to the layers that are underneath these layers. So that is the reason why the researchers and agencies have did some advancement related to asphalt layer. And the other thing is because this top layer, this asphalt layer is on the top, it is exposed to different environmental condition. So it ages due to the exposure to all the environmental condition. So if we look at the advancement related to asphalt layers, as I said, there are numerous advancement related to asphalt layers. I would like to take few example here. Some advancements are like binder modification, binder grading, super pave mix design, stone mastic asphalt, rutting resistant mix design, cracking resistant mix design, fatigue resistant mix design, aging resistant mix design, and so on. So these are like kind of advancement that were occurred in the recent decade. More specifically, if we see the advancement, which is the asphalt balance mix design process, this is like a kind of buzzword around the globe for the past 5 to 10 years. So what this asphalt balance mix design is, it's basically the process which aims to mimicking the rutting and cracking performance of asphalt mixes. So the asphalt layer basically fails primarily in two failure conditions. Those are rutting and cracking failure. So making these mixture resistance to rutting and cracking is called as the balance mix design process. How do we do that in our laboratory? So basically to make a mixture resistance for rutting and cracking, we need the basic materials, as we know, the binder and aggregates. Once we have these materials, then we prepare the asphalt samples, which consists of mixing process and compaction using a super pave gyratory compactor. Then based on the local test specification and test procedures, we have to run rutting and cracking test. There are numerous rutting and cracking tests that are available with the agencies. But here we use in the Texas, especially the Hamburg wheel test and overlay test to evaluate the rutting and cracking resistance. So this mix design process is like trial and error, and until the mix passes a specified rutting and cracking requirement, then this process will be done in the laboratory. So once the mix meets the rutting and cracking requirement, then the next step is to produce JMF, and then next the construction of asphalt layers will go in the field. So this is like kind of general procedure or general thing that we follow in our laboratory to make a asphalt mix design. But the question might be, is there any approach or is there any strategy to make a mixture resistance for rutting and cracking resistance? Yes, we do have approaches. These approaches were outlined in ASTO specification PP105. So we have four approaches we call as approach A, B, C, and D. Regardless of the approach, the main thing here is whether the mix meet rutting and cracking requirement or not. If a mix meets the rutting and cracking requirement, then next step is to evaluate the mixture moisture damage resistance. If it meets the moisture damage requirement, then the next step is to establish the JMF production. Since we have like a flow chart here, and I'm not able, I'm unable to go through all these details. So instead of that, what I would like to do is I would like to just highlight the mixed design factors that controls each approach. So if we take the approach A, that is completely dependent on the volumetric mixed design, and if one would like to go with the approach B, then the factors that need to be varied in the mixed design or volumetric mixed design plus additional binder content. In the case of approach C, it is related to aggregate gradation and binder content, and approach D considers aggregate gradation, binder grade, and binder content. So here the approach C and approach D, they completely eliminate the requirement of volumetric requirement. They are like special approaches, whereas they don't consider the volumetric mixed design process. Okay, so let's start and present little bit about the skid resistance. So if we look at the pavement hierarchy level, we have roughness at the top, mega texture next, macro texture at third, and micro texture at fourth. So this is like kind of hierarchy level of the pavement, how it starts from roughness at high scale to micro texture at very low scale level. The first two, roughness and mega texture, are related to comfort, and comfort is directly dependent on the stresses that are there on the pavement. So if a pavement shows rutting, cracking, or any other kind of failure, that will affect the comfort of the road user. So the comfort won't contribute to the skid resistance. The only two factors that contribute to the skid resistance are macro texture and micro texture. The thing that affects the macro texture is gradation of the mixture, whereas a micro texture is more specifically forced on the individual aggregate texture. So how this macro texture and micro texture generate the skid resistance is based on the hysteresis forces. So if you see here the figure, the macro texture, it causes a opposing force on the tire. That force on the tire generates skid resistance, and the micro texture generates adhesion forces. This is due to the tire and the individual aggregate particle interaction. So both these hysteresis forces and adhesion forces generate the skid resistance at the interface of tire and pavement surface. How do we evaluate the skid resistance in the field? That might be the question. Most of you already know about the skid trailer test, so I would like to play here a short video to show how a skid resistance of a pavement is evaluated in the field. This video is prepared by the OU Department of Transportation, so we would like to acknowledge them before playing this. So I would like to play this, and this video will give us an outlook, this video will show how a skid resistance is evaluated in the field.
To kind of see what's going on out there with wet car crashes. We use it as a tool to aid our district DSRTs and our pavement engineers to determine what may or may not be going on out there on the road. We'll push a button on the vehicle there to lock up the one trailer tire and put down a predetermined amount of water before we lock the tire up. We'll drag it for about 60 feet, and that'll give us a response, and it'll actually tell us what the texture of the pavement's doing as we're going down the road. And then from that information, the engineers can go back and determine if we have enough wet friction out there. It's all safe.
I think this is kind of a skid test that we do in the field to evaluate the pavement skid resistance. So the question might be, how do we evaluate in the lab, right? So to evaluate a mixture frictional resistance in the lab, we have a procedure that we follow. So before explaining this slide, I would like to tell when it comes to the field, I will say the skid resistance as a name, and when it comes to the lab, I'll say the mixture frictional resistance. So these are like skid and friction are the two names that were used technically in this field of pavement engineering. To evaluate mixture frictional performance in the lab, so what we have to do is, like as per the ASTO PP 104 specification, we have to prepare asphalt ring, as you can see in this slide. So to prepare asphalt ring, we need the super pave variatory compacted specimens. So once we have the compacted specimens, then we go through the steps that we are showing here from A to F in order to get the asphalt ring that we have in figure G. Once the asphalt ring that is shown in figure G is ready, then the next step is like polishing. So we use 3-wheel polishing device in our laboratory to evaluate a mixture frictional performance. So what the polishing device does is it basically kind of simulates the trafficking that happens in the field. Then to evaluate the skid resistance, which I call frictional resistance since this is lab. So we use dynamic friction tester to evaluate the mixture frictional performance. So these two devices work in tandem and gives us a friction deterioration curve, as you can see here. So to get this friction deterioration curve, basically what we have to do is once asphalt ring is ready, then we have to do the friction test, which is at unpolished conditions. Then we get the friction value at this point. After once we are done with the friction test, we have to polish the asphalt mixture using the 3-wheel polishing device for certain number of polishing cycles. Then we have to stop the polishing device. Again, we have to do the friction test. So once we are done with the friction test, again the things comes here is to polish the asphalt ring using the 3-wheel polishing device for certain number of polishing cycles. Then we have to stop and we have to do the friction test. So this stop and doing friction test process goes until the friction deterioration curve or the friction values become straight, which means that the mix reach the terminal friction value, and polishing behind that point may not decrease the mixture frictional performance. So this is kind of friction deterioration curve we generate in our laboratory. And if we have two mixes and if you want to see which mix is good, we compare the friction deterioration curve of those two mixes before judging the mixer's frictional performance. Okay, so if you see the presentation so far, I have started with the types of pavement. I have elaborated on flexible and rigid pavements. Then more specifically on flexible pavement side, I talked about the asphalt BMD process, its importance on the structural performance. Then on the safety aspects of the flexible pavement, I talked about the surface factor that affects the road user safety, which is based on the skid resistance. Okay, so let me move on to the significance of the study. So as we have shown in the title of this workshop, so we are trying to incorporate skid resistance into the circle, more specifically during the asphalt mix design stage. So far, any agency or any contractor, like everybody does a mix design process. At that point, they target at rutting, cracking, and moisture damage performance. And if the mix meets the rutting, cracking, and moisture damage requirement, then it goes to the field construction. But one thing that was not given much emphasis during this mix design process is skid resistance, which is especially the safety of road users. So we are trying to add this skid resistance as a part into this full circle. So when we consider this as our end goal to incorporate skid resistance into this circle, we found few gaps in the literature, and we thought these are the factors that are like stopping to incorporate skid resistance into this circle. So the factors here we found are like, if we have a poor frictional resistant mixer, so we don't know how to improve the mixture frictional performance. And the other thing is, like as I presented, the test method that we use in our laboratory, that takes almost like 50 hours. So agencies or contractors may not able to use those kind of test procedures, so we need a surrogate test method instead of the lengthy procedure that we have as per ASTO PP104 specification. Then the other thing we identified in the literature was we have a framework. Using that framework, we can make a mixture resistance for rutting, cracking, and moisture damage resistance. But we don't have a framework specifically on the skid resistance. So we thought, like, if we have a combined framework that considers rutting, cracking, moisture damage, and skid resistance, that will really help the agencies to incorporate skid resistance and to make a mixture resistance for skid resistance, rutting, cracking, and moisture damage during the mix design process. So to elaborate the things that I have discussed in the previous slide, so when we looked at the literature so far, we have seen the advancement related to the flexible pavement. More specifically, we have seen the asphalt balance mix design process that recently came to make the mixture balance for rutting, cracking, and moisture damage performance. So all these attempts are focused on the structural performance improvement. So the one thing that is showing like less emphasis during the mixed design process is the skid resistance. Then at second, to improve the mixture frictional performance, when we did the literature, we could able to see the factors that affects the rutting and cracking resistance. So here in the left hand side table, I am presenting the factors and how they affect the mixture rutting and cracking performance. I would like to take one example here that is related to binder percentage. So if we have a mixture that is showing poor rutting resistance, then to make that mixture resistant to rutting, what we basically have to do is we have to decrease, we have to go below the OBC. And if that mix shows or fails the cracking resistance, to make that mix resistance to pass the cracking resistance, what we have to do is we have to increase the OBC. So by doing these and uh, trial and error things and coming up with the binder percentage that will make the mixture resistance for rutting and cracking, that using that process we can make a mixture rutting and cracking resistant. Besides that, we have other factors like if we bump the binder grade, we can make the mixture resistant for rutting cracking resistance. And if we play with the air voids percentage, using that also we can make the mixture resistance for rutting and cracking. And we have other several factors we can use to make the mixture resistance for rutting and cracking resistance. So using these factors, we can improve the mixture rutting and cracking performance. But on the other side, to improve the mixture skid resistance, more specifically to improve the macro and micro texture, there are factors that we found through the literature study, but most of the factors were not studied as I highlighted here in this cells as NS. So there is like kind of gap in the literature to understand and to know how to improve the mixture skid resistance using the mixed design factors. Then at third, as I mentioned, this process that we follow in our laboratory, this process takes 50 hours. So this is like kind of not practical or feasible method for highway agencies or contractors. Not only the time, the other factor is the manpower and the initial cost and the operational cost of these devices to evaluate the mixture frictional performance. So there is a need to come up with a practical or surrogate test method instead of the process that we currently use in our laboratory. Then at fourth, as I mentioned earlier, we have frameworks to make the mixture and to improve the mixture rutting and cracking performance, but we don't have a framework to improve the mixture skid resistance. So if we have a combined framework that considers rutting, cracking, moisture damage and skid resistance, and if you use that kind of framework during the mixed design stage, so it will definitely helps to make the mixture resistance for all those four performance and that mixture will definitely perform better in the field when it is constructed and open to the traffic. So all these four gaps, to address these gaps, we basically came up with a research methodology. Since our first gap is like to improve the frictional performance, so what we did on our research methodology was we tried to vary each mixture parameter and we try to see what is controlling the mixture frictional performance. So once we did that study, we tried to perform some case studies in our laboratory and field friction studies. So the case studies and field friction studies are like kind of validating and verification of the parameters that we identified in our stage 1. Then for the polishing process, which is like takes 50 hours right now, to accelerate that and to come up with a surrogate test method, we came up with an accelerated test process and we formulated a model. So that model can be used during the mixed design stage to predict the mixture frictional performance. Then for the combined framework, we came up with an approach. So that approach considers skid resistance, rutting resistance, cracking resistance, and moisture damage resistance. So using that approach, a mixture can be made resistant for all the four performances. Okay, let me start with the results part of the study. Before beginning with the results part of the study, I would like to give a glimpse about the materials and test methods that we followed. So if I would like to show the materials that we have used, so we used 3 grades of binders in our study, and we used aggregates. Those are like 8 types of aggregates, which include limestone, gravel, dolomite, granite, rhyolite, sandstone, trap rock, and pyrite aggregates. And we used 7 types of asphalt mixers. Those are super pave coats, super pave dense, dense graded coats, dense graded dense, thin overlay mixers coats, thin overlay mixers fine, and stone mastic asphalt. And then coming to the test methods, we have a video demonstration on how to evaluate the mixture laboratory frictional performance. This video demonstration is prepared by our PhD student Mirza Amiskan. Now I'm gonna stop here with my presentation. I'm gonna play that video. It's like 20 minutes video, and that video demonstration will give visual experience on how to prepare asphalt ring, how to polish, and how to do the friction test in the laboratory. So I'm gonna stop and I'm gonna play the video that we have as part of this video demonstration.
Hello everyone, my name is Amish and I'm working as a research assistant at University of Texas El Paso under the supervision of Dr. Abdullah. My project is about the skid resistance of asphalt mixes. So this one is plant mix, lab compacted sample. The height of this sample is 62 mm. We can control the height in the lab, but when we go to the field to get some field course, we cannot control the height because sometimes the field cores are lower than 62 mm and sometimes field cores are higher than 62 mm. Both of these are field cores. So the thing that we have to make sure is that the bottom surface of the field cores is flat, because when you are placing them on the mold, they shouldn't be crooked. The top surface should be flat. So for that purpose, we have to cut the field cores to make them straight, to make them flat. So we select the most thinnest part of the field core and then we just cut it straight. And we do the same for this, but we just measure it up to 62 mm of height and then we just cut it. So once we are done, the next step is to cut the samples. So we have this is just a piece of paper, and the length of the upper side is 140 mm and the length of the lower side is 50 mm. So what we usually do is we just place it on the sample like this, and then we just mark it like this. So once we have marked it, you can see like this, right? So what we do after that, we just cut it through this line and this line, and we have to make sure that when we are cutting this, it should not be crooked, because when we will place it on the mold, there will be gaps, right, between the samples, and because of that, those gaps, the friction values will be affected. So I have these samples that we have cut. So you can see that the sides are straight, right? And when we put them on the, it should be like exactly like this, see, like touching each other. So that's the thing. So this is an empty mold here, just to show how do we do it. So I will place the samples here. Just have to put it, and we can see the height is the same. We can also use the scale just to make sure. But since I have been doing it for a long time, so I'm just used to it. We usually make 8 samples so that there is always an extra one if some of the samples is not good or it's crooked or something like that, just to be on the safe side so that we don't have to do it. That's how we just place the samples in the mold. And you can see that the samples are good. We just rearrange it. We have to make sure that all the samples are in the middle of the mold, because the DFT will be here, and it's in the if it's in the center, it will be good. Like it will be good, right? The results won't be affected. Also, we put the mold under the 3-wheel polishing device, so the peel path is on the right one. So what I usually do is, after placing the molds like this, after placing the samples like this, I usually run a finger like this, so that we can make sure that none of the samples is higher. There is no difference in the heights of the samples. So yeah, this is good, right? So, and what about this field work? So once we have cut it, once the base is a flat surface, what we usually do is we sometimes put the sand in this mold, and then we put the samples on the sand, like especially the samples that are lower than 62, and then we usually we hit the samples a little bit with the rubber hammer, so that the sand is compacted. After that, we pour the cement on the mold. So that's how we do the samples that are lower than 62. You have to make sure that the height of the samples is up to 62 millimeters, like same like the mold itself. So that's how we do it. And then once you have done this, you just have to pour the cement in this mold, and like here in the middle and also on the sides, and make sure that the level of the cement is as much high as possible. As we have already marked the sample, the next part is the cutting part. So we have to make sure that there is no smaller aggregate or something on the cutting machine, because it will affect the cut. It has to be like lying straight on the cutting machine. You have to be very careful about that. Even a little aggregate or a smaller aggregate can affect the cut. It will get crooked. So once you are done, we place the sample on the cutting machine. We put it as much as closer to the cutter, and by using a scale, we align the line and the cutter so that it's straight. So once we are done, it's straight. We make sure that it's not moving, and then we just very slowly. And then we just turn it off, and then we remove the sample, and again we have to clean it because there are little particles in the cutting machine. We have to clean it very thoroughly, and then we can put it again like this, and then see, like now see, it's moving. So that's the reason there was something below the sample, and if you put it, it is moving, see, like this. So that's why it's very important to clean the cutting machine. should not move. Still. Now it's not moving, so now it's good. Again, we have to align it with the cutting machine. We don't have to press it against the blade, we just have to place it. Otherwise, it will affect the alignment. Now it's exactly at the line that we marked. That's how we can cut the sample. Now, as we can see, it's not crooked, it's straight, exactly straight, as we can see. Right. So now, once we have arranged all the samples, the next part is we have to pour the cement. That's how we do it. We pour it slowly. Now it looks perfectly fine. The height is good, the cement level is good, everything is good, and now it's good to test. Like, we will leave it overnight, and when we come tomorrow, it will be dry and ready to be tested. Alright, so here is the dynamic friction tester that we use to test the friction of the asphalt mixes. We also use it for the friction of aggregate rates that we make. So I will tell you about the steps of this. So this machine has 3 pads here. So when you run it, it goes up to a speed of 80 km/h, and then after that, this plate, it falls on the specimen. So while it's going to that speed, the water, it starts throwing water from these holes on the sample, and then after that, like when it falls on the specimen, it measures the friction of that specimen. So we usually test the test up to 200 tests. After that, we change these pads because these pads, like, they have a life, so the friction results start to decrease. So that's why we have to change these pads after every 200 tests. So that's how we run it. And this now, we usually when we are transporting the machine or like moving the machine, machine, we have to put it like this, and during the test, before the test, we just have to remove it and then run the test. So that's all about this machine, and now we will run the test and then we will see like how it works. For the DFT, we have two outlets here. One is the USB and the other one is the power outlet. Usually use a battery for this power outlet, and this lead, it connects to the laptop so that the data can be run. So the first step is that we move the DFT. Since it's the first time we are running this sample, so we have to make sure that it's going to be done. Yeah, like that. Once we have placed the sample, what we do is we mark the location where we are placing the DFT so that the next time we run the test, it's not at a different location. So that's why we always mark the location where we are placing the DFT. Once we are done with that, as I discussed about the cables and this knob, so we remove this knob and then we just connect the cables. The first cable for data is connected to the DFT and the power outlet. Then we have is this one. So once we are done with the power outlet, the next step is that we have to connect the hose to the DFT. It's connected with the tank, so it supplies the water to the DFT, and it has to pour the water on the sample. When it runs, it will start pouring the water. That's how it gets the water supply. Now the DFT is running, and it will reach up to 80 kilometers, and then a plate that's rotating below it, it will fall on the sample, and that's how it will measure the friction of the sample. And the water, it usually starts coming out of the DFT when it reaches up to the speed of 60 km per hour. That's how the test started, and as you can see, like when the plate falls on the sample, it is rotating and it stops due to the friction of the sample. So as I mentioned, that we usually run 3 tests. So this was first test. We usually wait just for 30 seconds or up to 1 minute before we can test another class. So now we will run another track, second track. And go up to the speed of 30 kilometers and then it, and after that we will just plot the values and we'll take the average of the pretest at a speed of 60 km per hour. So once the test is done, what we do is just put the top back before we move it. Then when the machine off, we remove the outlets, both the USB and the power outlet. Then remove the tools. Once the specimen is in, we can just start running the needle polishing device. So I have set the cycles up to 1000 cycles. And so what I usually do is I also mark it a little bit here so that when I put the sample out of the needle polishing device and test it for DFT, and I have to put it back, it should be exactly at the same position so that there is no variation in any of the results. So now you just have to run it, and that's how it starts polishing. As you can see, it will take up to 15 to 20 minutes for just 1000 cycles. So when you have more cycles, like 25K cycles or 50K cycles, you just overnight, and then you just run the next time.
All right. So as we have demonstrated in the video, this is how we prepare the asphalt ring and we do friction test and polishing process. So I would like to show an Excel file which explains how we generate the friction deterioration curve. Okay, so as Amish mentioned in the video, like we do 3 friction tests. So if you see column B, C, and D, these are the friction values for the pre-test. And in column A, we get the speed. So the friction values corresponding to each speed we have in B to D. So we get the friction values from 80 kilometers per hour to 10 kilometers per hour. And then at 10 kilometers per hour, the DFT stops on the asphalt ring. So in this data, the main things are 60 kilometers per hour friction values, 40 kilometers per hour friction values, and 20 kilometers per hour friction values. And the reason why we consider these are because ASTM E1911 specifies to report these values as friction values of a given sample. So once we have this raw data, we just do some standard deviation and averages and coefficient of variations to see how the 3 tests are varying in terms of their standard deviation and coefficient of variation. So this process we do until 300K polishing cycles. As I mentioned in the presentation, we do polishing and we stop at certain number of polishing cycles and we do again the friction test. So the sheets that you can see here at the bottom are related to polishing cycles at corresponding cycles. Then once we are done at the 300K, we then generate the friction deterioration curve. I would like to show an example how we generate the friction deterioration curve. So basically here the B column is the cycles, that is 3 wheel polishing device cycles, and C here is wheel passes. So one 3 wheel polishing device equal to 3 wheel passes because it has 3 tires. So we are just wrote here the in terms of wheel passes. Then we got here the DFT values. Those are dynamic friction values at 60 kilometers per hour, 40 kilometers per hour, and 20 kilometers per hour from the corresponding polishing cycles Excel sheets. We did the average here for the 3 values. And here we just generated, just like prepared the graph that is a three-wheel polishing device cycles versus DFV. And usually like we use 60 kilometers per hour in our reports and presentation, because as we know the crashes more specifically happens at high speed, so that's why we consider DFE value at the rate of 60 kilometers per hour. So as we can see, this is like kind of raw data. As you can see, there is some noise, so we don't use this graph directly into our presentation or report. We do a curve fitting process to this in order to make this like look smooth and clean. So for that, what we do is once we have these values, we do power fit curve fit for this. The reason why the power fit is because when we looked at mixers friction deterioration curves for almost like 50 mixers, we found that power fit is a good curve fitting process for the friction deterioration curve. Then once we do the power fit, then we generate the equation. So here y is nothing but the friction value. X is three-wheel polishing device cycles. So these are the values after the curve fit process. Usually at 0K, we don't do power fit. We just consider the raw value that we have here in the data. The reason is because in the initial process, there will be binder that is present on the asphalt surface. So if we do the curve fit process also for this, the value will significantly increase. So if you see the raw data, it is showing 0.39, but the power fit is showing 0.47. So since as we can see, there is much increase in the friction value due to the power fit process. So we don't do power fit at 0K. We just check directly the raw data value that is 0.39 in this. Then next step, what we do is we plot the graph for the power fit. And as you can see how good the curve looks, and let me take these. So as you can see how good the friction deterioration curve looks. Okay, and these graph we use in our presentations from now onwards, like when I'm going to present the friction deterioration curves. So one question might be, some of you have, does this curve fit process affects the friction deterioration curve? No. When we looked at 50 mixers, we found that the per fit terminal friction value and the raw data terminal friction values are almost same. And as we know, our importance in this friction deterioration curve is the terminal friction value, and we can see here 0.21 in the case of raw data and 0.21 in the case of our process. So whole thing is just we are like smoothening the curve using the power fit process instead of using the raw data. This is about the curve fit process. Let me go back to the presentation. Okay. So as we have demonstrated in the video, so this is a process that we do, the ring preparation process and the polishing device. I would like to again mention that we strictly followed the ASTO PP 103 specifications. There are few changes that we did for the ring preparation process and the polishing condition because of our research needs and to make the testing process easy in our laboratory. And the friction test we did as per ASTM E1911, and we did wet friction test. As we know, the frictional performance or the skid performance is low under wet condition when compared with the dry condition, and we did friction measurement at these polishing cycles. In addition to the frictional performance for the asphalt mixers, we do also perform the rutting test as per ASTM 2019A, and we did cracking test as per ASTM WK26816, and we did moisture damage test specifically to simulate the moisture damage for the asphalt mixers as per ASTM D6931, which considers moisture-induced stress tested device for simulating the moisture damage in the asphalt mixers. So before jumping into the results in detail, we would like to give a 10 minutes break, and after that we will continue the presentation to show how we improve the mixture's frictional performance when it is having very poor frictional resistance. So I would like to stop here and give a 10 minutes break, and after that we will continue.
Hey, we're back. I just wanted to thank everybody for being part of this presentation. Before we continue, I just wanted to thank Sandeep. We talked about it a little bit about mixed design, and he went into a lot of detail on how we carry out this test and showed a video of how we prepare our samples. By the way, there are several ways of preparing. You can prepare a slab and cores. We chose to go preparing samples using cores, and I think our DOT is following along with that. It allows us to do cores from the field or prepare samples in the lab with the same setup. So the next part that Sandeep will present is going to focus on a controlled experiment. Now that we have a test that can measure the terminal friction value, and that's where we started. The interest was to look at the terminal friction value of the mix. What are the parameters that can affect that? What parameters are going to affect that terminal friction value in terms of the mix design, the binder, the air voids, and so forth? So he and his colleagues put a really good controlled experiment, and then he's going to go over that with you guys. And then later we will talk a little bit about the aggregate. And then the final part of the presentation would be how did we progress to come up with a method that will speed up this testing. He mentioned that this test, is over 40 hours long, so it is time consuming. For a DOT, they would rather have something a little bit faster, and we'll discuss some of that, some of those studies that we have come up with. So Sandeep, I'll turn it back to you.
Okay, doctor. Can you hear me, Dr. Abdullah?
Yes.
So from now onwards, I'm going to talk about the results related to asphalt mixture frictional performance. So these results are main part of our study. First, I'm going to talk about the 4.1, which I am calling here as parameters controlling the mixture frictional performance. And I'm saying here a control study because usually when we get a mix design, we know that we have different aggregate types in the mix. For example, if you see the mix design that I'm presenting here, it has 5 bins, and the last bin, that is sixth bin, was a wrap. So if you want to know what is controlling the frictional performance in this type of mix design, we couldn't able to, we won't get exactly what is happening, because it has wrap, it has mortar sand, it has igneous aggregate, it has limestone. So there are many things are there in this mix design. So in order to make the mix design control and to understand better what is controlling the frictional performance, we tried to convert this mix design into a control mix. So for that purpose, what we did was, as you all can see here, we separated the bin 1, bin 3, and bin 5, which were limestone dolomite aggregate, and all these are from same parent rock. So once we separated these, we sieved, and the sieved aggregates we kept in different buckets. As you can all see at the right side, we have the limestone dolomite aggregate from top size to the pan, and all these are aggregates from the same parent rock. So from then here onwards, we took these aggregates and we prepared a asphalt mix in the lab, and then we tried to vary each mix design parameter to see what is controlling. So so with this process, we'll have complete control on the mix design, and we can easily know what is affecting the mixture frictional performance. So we used control mix in this study. Then when we were trying to look at the factors that affects the mixture frictional performance, we separated these into three categories as material related, mix design related, and construction related. We have a publication which is in production. You can refer this in the near future when it's like open to the readers. So in the material related parameters, first we try to understand the effect of binder grade. So we considered three binder grades. Those are PG6422, 7022, and 7622. And we prepared three asphalt ring, and we went through the process as we elaborated in our video, the polishing process and friction test. And as you all can see here, these are the friction deterioration curves for the three mixes which are prepared with three binder grade. And we can see here that the effect of binder grade is negligible, which means that all the three friction deterioration curves are close to each other. In terms of t-test also, it showed that the difference between these three friction deterioration curves is insignificant. Then we looked at the effect of aggregate type. We prepared two mixes. In one mix, we used completely limestone aggregate, and in another mix, we completely used sandstone aggregate. When we evaluated the mixture frictional performance, we found that the mix that is having sandstone is showing high frictional performance, whereas a mix that is having low frictional resistance, mix that is having limestone is showing low frictional resistance. We did some mineralogical study, and we found that sandstone has high hardness minerals. Those are in terms of mode scale. So that is the reason why sandstone aggregate is performing well in terms of frictional resistance. It also proved as per t-test that this difference between these two friction deterioration curves is significant. Then under mixed design related parameter, we tried to vary the binder content. So the OBC was 5.1%. We went and we selected 1% below OBC, that is 4.1%. We went 1% above OBC, that is 6.1%, and we went 2% above OBC, that is 7.1%. And what we observed was all four friction deterioration curves are close to each other, and this was also showed that the difference between the four friction deterioration curves is insignificant as per t-test. So the question might be like, is it binder like it doesn't it affect the mixture frictional performance? Yes, it does affect, but that effect will be only at the initial polishing cycle fails, because binder just forms as a thin layer on the aggregates. So once we start the polishing process, the binder will wear off from the surface, then all the four friction deterioration curves were becoming close to each other. Then under the mixed design, we looked at the effect of aggregate gradation. And in this, we kept the aggregate types same in all the three gradations. We considered coarse gradation, intermediate gradation, and fines gradation. And we found that all the three friction deterioration curves are almost close to each other, which was also proved as per t-test that the difference between these three curves is insignificant. Then we looked at the effect of mixture type. we considered 4 mixtures that were commonly used here in the state of Texas. Those are super pave coats, super pave dense, dense graded coats, and dense graded mix. In all these 4 mixes, the aggregate type is same, which was limestone dolomite aggregate. And we found that the 4 friction deterioration curves are close to each other, which means that the effect of asphalt mixture type on the frictional performance is minimal. This was also proved as per t-test that the difference between the 4 curves is insignificant. Then we looked at the construction related parameters, that is effect of air voids percentage. We prepared 2 mixers. One is compacted at 7% air voids and another we compacted at 3% air voids. And we found that the 2 friction deterioration curves are almost close to each other, and the t-test showed that the 2 curves difference is insignificant. So the reason why the air voids are not contributing to frictional performance is because the air voids are internal parameter of a mixed region, so they don't contribute anything to the surface. So the factors that we studied in this control study showed that only the aggregate type affects the mixture frictional performance, and all the other remaining parameters effect is negligible to minimal. So the key thing here is, if we have a mixed region on our table which is having poor frictional resistance, to improve its frictional resistance, we have to switch the aggregate type by considering a good frictional resistance aggregate. So that's how we can improve the mixture frictional performance. Then we took this effect of aggregate type study to the next level. So we went to the complex stage. So what we did in this case was we tried to understand which portion is controlling within the aggregate gradation. We separated the gradation into 3 portions as codes, intermediate, and fines. And then we tried to understand which portion is contributing to mixture frictional performance. I would like to go step by step through this table. So first we prepared 2 mixes. One is mix 1 and another is mix 2. In mix 1 we kept 100% limestone aggregate, which means coarse, intermediate, and fine portions are limestone in that mix. Then in mix 2 we considered sandstone as aggregates 100%, which means the coarse, intermediate, and fine portion all are sandstone aggregate. And in all these six in these mixes there is no any wrap on any of the motor sand or anything. All the aggregates are from same parent drug, so we could able to understand what is controlling the mixture frictional performance. So if we when we looked at the mixture frictional performance, the mix 2 that is having 100% sandstone showed almost like 0.40 terminal friction value, whereas the mix 1 which is having limestone aggregate showed 0.25 frictional value. Then at the next stage, we prepared another 2 mixes to see which portion is controlling. In mix 3, we kept limestone 50% in the coarse portion, and the remaining 50% was sandstone, that is in intermediate and fines. Then in mix 4, we kept sandstone in the coarse portion, that is at 50%, and we kept limestone in the intermediate and fines portion. So what the mix 3 and mix 4 tell us at the end is whether the coarse portion is controlling the mixture frictional performance, or intermediate and fine portion is controlling the mixture frictional performance. So when we looked at the study results, we found that mix 3 showed the terminal friction value close to mix 2, which is having 100% sandstone aggregate. So main finding here is just by using 50% sandstone aggregate in intermediate and fine portion, we are getting almost close to whatever we get when we use 100% sandstone aggregate. Mix 4, which is still having 50% sandstone as same as mix 3, but in the coarse portion, it showed terminal friction value of 0.31. So 3 and 4 are having 50% sandstone in both mixes, but one is showing 0.31 terminal friction value, other is showing 0.37 terminal friction value. So much contribution is coming from intermediate and fine portion than the coarse portion. Then at next level, we prepared another 2 mixes. Those are mix 5 and mix 6. So the objective here is to see whether the intermediate portion is controlling or fines portion are controlling. Since the objective is to understand intermediate versus fine portion, we kept coarse portion as constant with limestone aggregate, which is at 50%. So then in mix 5, we kept 36% limestone in the intermediate portion, 14% in the sandstone in fine portion. In mix 6, we kept sandstone at intermediate portion, that is at 36%, and limestone in the final portion at 14%. So we'll know whether the intermediate portion is controlling or fine portion is controlling. So when we looked at the study result, the terminal friction value of mix 6 was found to be 0.36, which is again close to the mix 2, which is having 100% sandstone aggregate. Whereas mix 5, which is having 14% sandstone in fines, it showed 0.26 terminal friction value, which is close to mix 1, that is having 100% sandstone. So the main thing, our main finding here is the mix 6, which is having 36% sandstone, it showed 0.36 terminal friction value, whereas mix 2, which is having 100% sandstone, it showed 0.40 terminal friction value. So just by using 36% sandstone aggregate in the intermediate portion, we can achieve the frictional performance that we get with the 100% aggregate as we have seen in the mix 2. Then we try to analyze like why this intermediate portion is contributing much to the frictional performance than the codes and fines. Then our analysis showed that the surface area of intermediate portion is high in comparison to the codes portion. That is the reason why the sandstone that is there in mix 6 contributing much to the terminal friction value. To demonstrate this surface area effect, we took sticky notepad and we kept 10 grams of aggregates that is retained on each sieve size on the sticky notepad, and we took pictures. So these sticky notepads are general that we use in our office purpose to take some notes. So here we can see the A part, that is 19 mm aggregate, retained aggregate. This is 10 grams of aggregate, so we got one aggregate, and this is the surface area that is covered by this size. And for the 12.5 mm, this is still again 10 grams of aggregate. It covered, we got two aggregates and it covered little bit of more surface area than 19 mm size. Then for the 9.5 mm, this is still 10 grams of aggregate. We got 5 aggregates and it covered more surface area than 12.5 mm sieve. Then for 4.75 mm sieve size, this is still 10 grams of aggregate. We got 10 aggregates and it covered almost like 60 to 70% of surface area of the sticky notepad. As we can see here for the codes portion, that is A, with the decrease in the sieve size, there is an increase in surface area. For the intermediate portion, this is for 2.36 mm sieve size. This is still again 10 grams of aggregate. This is covered almost 80 to 90% of sticky notepad. So we can see here the difference. The 19 mm, we got only one aggregate and this covered this much of surface area, which is 10 grams. And here this is still 10 grams. It covered almost 80 to 90% of sticky notepad. For 1.18 mm sieve size, the 10 grams covered almost like entire sticky notepad surface area. Interestingly, for 0.6 mm, the 10 grams of aggregate retained on 0.6 mm sieve covered two sticky notepad instead of one. So if we see here the intermediate portion, it covered and it is having high surface area in comparison to the codes portion. So if I put all these aggregates, I can keep those aggregates here because I have still place. So the 40 grams of aggregates of codes portion, it is gonna cover only one sticky notepad, whereas the intermediate portion, 30 grams is gonna cover 4 sticky notepads. So it is like 1:4 ratio, the surface area it is covering. And you might have question like, as we can see here, the fines are having high surface area. For example, 0.3 mm, 10 grams of aggregate written on these sieve size, it covered 3 sticky notepad. And for 0.075 mm, it covered 4 sticky notepad. And for pan, it covered 5 sticky notepad. Even though the fines are covering more sticky notepad and having more surface area, they are not controlling the mixture frictional performance, because these are very fine particle and they will wear off from the asphalt surface after initial polishing cycles. And the other reason is because these are fine particle, they don't generate hysteresis and adhesion forces between the DFT and the asphalt surface. So we have only codes portion and intermediate portion on the asphalt surface. Since intermediate portions are having high surface area, they are contributing much for the frictional performance than codes portion. So this is how we can improve a mixture frictional performance. If we have a poor frictional resistance, just by targeting the intermediate portion of the aggregation and by replacing it with a good frictional resistance aggregate. This is about the 4.1 study results on how can we improve a mixture frictional performance. And then we tried to do some case studies on the typical mix design. As I have said in the previous slide, we considered the control mix. Then we went back to the typical mix, which is having different bins and different aggregate types in the mixes. We did 3 case studies. So here our goal of these case studies was to verify and to do some kind of research validation based on our control study findings. So in these case studies, what we did is we targeted the intermediate portions of the gradation and we replaced the intermediate portion with some good frictional resistant aggregate. So in the case study one, we considered super pave mixtures. So the purple one here is a collected ASPC mix, which we collected locally from the contractor, and it showed a terminal friction value of 0.26. So in this case study slide, I'm gonna show in the column graph, and more specifically, I'm gonna talk about the terminal friction value because the main emphasis is on the friction deterioration curve is the terminal friction value instead of all the friction values on the curve. So we got a terminal friction value of 0.26 for the collected SPC mix. On the other extreme side, we completely replaced the aggregates with the sandstone aggregate and it showed 0.40 terminal friction value. That is a blue one. So to improve the collected SPC mix frictional performance close to the SPC mix with 100% sandstone aggregate, what we did was we targeted the intermediate portion of this collected SPC mix and we replaced the limestone aggregate that was sitting in the intermediate portion with sandstone aggregate at 40% and it showed 0.35 terminal friction value. So as we can see, this is kind of like validation and verification of what we observed in our control study. So basic thing here is just by using 40%, we are getting almost what we get with the 100% sandstone aggregate. Then in case study 2, we considered a thin overlay mixture. The collected SPC thin overlay mixtures showed a terminal friction value of 0.12, which is very low. And on the other extreme side, in the blue one, we are having a thin overlay mixture codes, same gradation, but with the sandstone aggregate, and it showed a terminal friction value of 0.42. Then same as case study 1, we targeted the intermediate portion of the collected thin overlay mixtures and we replaced it with the sandstone aggregate at 34%, but we couldn't able to see the frictional performance, the terminal one, close to the one that is having 100% sandstone aggregate. So the reason why this is not close to this is because the gradation here and the mix type is thin overlay mixture coarse mixture. Since it is coarse mixtures, it is taking much coarse portion, not intermediate and fine portion. So the more aggregate is going into the coarse portion, so it is not contributing close to the mixture that is having 100% sandstone aggregate. So to overcome this problem, what we did was we changed the mixture gradation. We changed it to thin overlay mixtures fine gradation and we targeted its intermediate portion and we replaced the intermediate portion with sandstone aggregate at 38%. Then we could able to see the terminal friction value close to what we get with the 100% sandstone aggregate. So just by using 38%, we are getting almost close to 100% terminal friction value. Then at last we did another case study, that is case study 3. We used again the super pave mixture, but here we try to play with the wrap material. So the collected SPC mix showed terminal friction value of 0.26 and on the other extreme side we completely replaced the aggregates with the 100% high friction wrap and it showed a terminal friction value of 0.35. So in order to improve and in order to prove our concept, we targeted this mixture intermediate portion, the collected mixture, and then we replaced it with the high friction wrap in the intermediate portion at 40%. Then we could able to see a terminal friction value of 0.32, which is very close to the mixture that is having 100% high friction wrap. So all these 3 case studies shows like a proof of concept of proof of our research, like kind of validation and verification that the intermediate portion controls the mixture frictional performance instead of coarse and fine portion. This is just for these mixture type. If you have a stone mastic asphalt, this may not applicable to that, and if it is If we have a open graded mixtures, these may not applicable for that, because those kind of special mixes have less amount of intermediate and fine portions. Then at next, we try to go to the field and to verify our lab results. So our objective here was to see whether the aggregate type is still controlling the pavement frictional performance in the field or not. So for this purpose, we went to the field and we collected friction data for different field test sections that are there across the state of Texas. We went with our DFT and we collected the friction data on the wheel path. So we targeted the test sections that are next to each other with different binder grades, with different aggregate types, with different binder content, aggregate gradation and asphalt mixture type. And our field study again showed the same findings that we observed in our lab, that the aggregate type affects the mixture field frictional performance. We couldn't able to find the field test sections with varying binder content, because as we know, agencies won't construct test sections by varying the binder content. They just they stick only to the optimum binder content. Then at next section, so we have 4.4. Here we tried to come up with some surrogate test method. So far in the result section until 4.3, we have seen how can we improve a mixture frictional performance during the mix design stage. And that is like we have to target the intermediate portion of the aggregate gradation. Then the next come is like to come up with a practical test method as a surrogate to the test process that we currently have, and as per SOPP 1004 method, which takes 50 hours. So what we did was we tried to analyze the friction deterioration curve for asphalt mixers, and what we found from our study was after 25K polishing cycles, the friction deterioration curves will become linear. So we try to do a power fit for the friction data that we collect until 25K cycles. Using that power fit function, we try to predict the terminal friction value of that asphalt mixture. So this process takes 16 hours, and in this process, we don't need to polish and do any friction test between 25K to 150K. And we stopped at 150K because our study showed that 150K terminal friction value and 300K friction values are almost same. There is no much difference. And though PP104 specifies to stop at 110K polishing cycles, we were doing up to 150K, and in the previous sections as I showed, we went up to 300K even. But after seeing the large amount of data set, we found that 150K is enough. And in this accelerated test method, we just collect the friction data up to 25K, and we do these points to predict the terminal friction value. So when we did this process, we found from our study that the measured one, which is through the ring preparation, polishing, and friction test process, and the ones that are predicted using a power fit method, are almost close to each other. And these research study findings are published in the Journal of Testing and Evaluation. You can refer if you would like to get to know more details about the study results finding. So this is how we can accelerate the test process, and we can reduce the test time to 16 hours instead of doing for 50 hours. Then at next phase, we try to develop a multiple linear regression model. To develop that model, we did a extensive laboratory study. So we did first was we tried to understand the effect of aggregate gradation on the mixture, friction, rutting, cracking, and moisture damage performance. So we kept the aggregate type in all these mixtures same. So we tried to see what is the effect of aggregate gradation on the mixtures performances. We considered 6 mixture types, which includes SPC, SPD, DGC, DGD, thin overlay mixture fine, and SMSE. And as we can see here, the effect of aggregate gradation on the mixture terminal friction value is minimal. That is why I highlighted here these cells in light color, whereas the effect of aggregate gradation on the mixture rutting, cracking, and moisture damage performance are significant. That is why I highlighted here the cells in the dark color. I'm not gonna go into detail about these numbers. There is a lot of information in this, but the main thing here is the effect of aggregate gradation on the mixture frictional performance is minimal, whereas its effect on the other performance is significant. Then at next stage, we try to understand the effect of aggregate type on the mixture's performances. We consider two mixes with same gradation, which were having one mixture is having limestone and the other mixture is having sandstone. So we try to see the effect of aggregate type on the performances. We considered like by varying the binder percentage, that is 4.1, 5.1 and 6, and for also same for the sandstone mixture. As you can see, the effect of aggregate type is significant on the terminal friction value, whereas the effect of aggregate type on other mixture performances are minimal, as I highlighted in light color in this. So the effect of aggregate type is significant on friction value, whereas its effect on other performance is minimal. Then we try to formulate a MLR model, and as we have seen from our extensive study that we did by varying the aggregate gradation and aggregate type, the gradation has minimal effect, whereas aggregate type has significant effect. So we came up with the variable fit alpha and beta parameters. So this kind of consider the gradation effects in the regression equation. And then for the aggregate type effect, as we have seen in our control study, surface area affects the mixture frictional performance, and that to the aggregate that is retained up to 0.6 mm controls the mixture frictional performance. We considered surface areas of these gradations. We came up with the surface area factor for each sieve size, and we multiplied with the aggregate friction value corresponding to each aggregate size. So then we came up with the combined aggregate friction value as a parameter from the aggregate side. We use CAAF, alpha and beta, and we came up with the MLR equation. And this MLR equation predict the asphalt mixture terminal friction value at 150K polishing cycles. The major significance of this MLR method is like we don't need to prepare asphalting, we don't need to polish, we don't need to do any friction test. If we just if we have a gradation, if we just add the alpha and beta parameters of the variable fit of the gradation into this MLR equation and the combined aggregate friction value, then we can predict the asphalt mixture terminal friction value. When we looked at the model performance showed that the measured and predicted ones are close to each other. Here we are presenting the training data set results. So total we considered 50 mixers. We separated into 70:30 ratio. 70% mixers we considered for the training data set and another 30% we used for testing the model performance. As we can see in this slide, the measured and predicted one are close, and none of the mixture terminal friction value error is above 0.10. And as per statistics, 88% of these mixes absolute error is less than 0.05. When it comes to the testing data set, we observed that the measured and predicted are again close to each other. And again, we haven't seen any mixture terminal friction value error above 0.10. And as per statistic test results, 86% of mixes absolute error are less than 0.05. So this MLR model can be used as a surrogate to the sample preparation, polishing, and test process. Here we are presenting in terms of scatter plot to see how these are well fit in the line of equity and how good the R square values is. On the left hand side, the R square value is 0.90 for the accelerated test method. As we know that the measured method, it takes 50 hours, whereas power fit method, that is accelerated test method, it just takes 16 hours. And then other side, the R square value of the MLR model is 0.710. So R square value is 0.70. If we do as per the clusters, and as we know that the friction values are categorized from 0.10 to 20, 20 to 30. So most of the mixed frictional performance were falling within these categories. So even though the R square value is 0.70, but they are falling within that category. As I presented earlier, that the measured method takes 50 method whereas this MLR model just take 0.5 hours. So there is a significant reduction in the time to evaluate a mixture frictional performance. Then at last, as part of this section 4 study, an approach. So we have an approach as per ASOPP specifications for BMD process to make a mixture resistance for rutting and cracking resistance. And as we found as part of this research study a gap that we don't have a framework or an approach to make a mixture resistance for friction, rutting, cracking, and moisture damage. So we came up with an approach. This is just like kind of a proposed approach. So we have two phases in this proposed approach. Phase 1 considers as an approach for skid resistance, and in phase 2 it considers an approach to make the mixture balance for rutting and cracking performances. So before going into details in this, let's consider if we have a trial mix design or an agency or a contractor as a trial mix design. And if they wanna know the frictional performance, they can predict the trial mix design frictional performance using the MLR model that we formulated. Then the one can see whether it is meeting the frictional performance requirement or not. If it meets the frictional performance requirement, then it is just a suggestion as part of this proposed approach to do the polishing and friction test. There they can use the accelerated test process by doing the power feed until 25K polishing cycles. If it meets a frictional performance requirement, like based on the test results, then it goes to phase 2. In any of these two stages, if it does not meet the frictional requirement, then one what has to do is they have to vary the high friction resistant aggregate percentage retained on 0.6 mm, because based on our control study we found that aggregate type affects mixture frictional performance, especially that is there in the intermediate portion and above 0.6 mm. So if they increase or if they replace low friction resistant with high friction aggregate, and if they increase aggregate content in that portion, it will definitely improve the frictional performance and it will pass through these requirements. So once it passes the requirement, then it goes to the next phase. So in the next phase, one what has to do is to perform the BMD process using one of the four approaches that we already have. After doing the BMD process, then and one has to check for the rutting and cracking requirement. If it meets the rutting and cracking requirement, then it goes to the moisture damage test. And if it meets the moisture damage requirement, then it goes to the JMF production. If in case if the mix does not meet the rutting and cracking requirement, there are few suggestions and few things that can be used in order to make the mix to pass the rutting and cracking requirement. If a mix does not meet the rutting requirement, so the one has to bump the binder grade and or decrease the binder percentage and or decrease the percentage of aggregate passings 4.75 mm. So based on our study results, we found if these are varied, then that will make the mixture uh, uh, resistance for rutting resistance. If the mix does not pass the cracking requirement, then one has to bump the binder grade and or decrease the binder percentage and or increase the VMA of mixture. So using these uh, approaches, the mix rutting and cracking resistance can be improved. But here we have a caution here. At this stage, one should not change the aggregate type in the mixture. If they change the aggregate type in the mixture, then that is going to affect the phase 1 results, that is frictional performance. So aggregate type should not be changed at this stage. If the mix does not meet the moisture damage requirement, then one has to add the anti-strip agents. And as we know that by adding anti-strip agents, the moisture damage performance will be improved. And some of you might be having questions whether these anti-stripping agents addition will affect the frictional performance or not. As far as like my knowledge, I would say these won't affect the mixture frictional performance because the anti-stripping agents are very fine particles and they will veer off from the surface and they'll go inside the asphalt mixtures, not much onto the surface. So they may not affect much the mixture frictional performance. So if it meets the frictional moisture damage requirement, then it goes next to the JMF production and for the field pavement construction. Okay, so to fit the skid resistance into this circle during the mix design stage, we found some gaps and we went through the research methodology and we have results to address those research gaps. So using these results, agencies can try to incorporate skid into this full circle during the mix design stage. So to improve the mixture frictional performance, one has to target the intermediate portion. In order to have a quick test method, power fit method can be used, or the MLR model that we formulated that can be used, which needs aggregate gradation and aggregate friction values as independent variables. And we also proposed a combined framework that can be used during the mix design stage to make the mixture resistance for friction, rutting, cracking, and moisture damage performance. So in this entire thing, the one thing that we are left is aggregate friction value. And in the next slides onwards, I'm going to present about how we evaluate the aggregate frictional resistance in the lab. And if we have the aggregate friction value, then we can use that in the MLR equation to predict the asphalt mixture terminal friction value at 150K polishing cycles. So now I'm going to talk about the friction test that we have, and these are like alternative aggregate friction test. So first thing as part of this section is the conventional test method. So we already have a specification that is ASTO PP103 to evaluate the aggregate frictional performance. So as per this test method, what we have to do is, if we have washed and dried aggregates, we have to prepare the aggregate rings, which consists of placing the aggregates inside the mold and pouring a binding material. And after that, we'll get this aggregate ring. Once the aggregate ring is ready, then it goes into the polishing device, same as the way that we do for the asphalt mixers. Then we also do the friction test and we get the aggregate friction deterioration curve, as you can see here. The major drawback of this method is like it takes 43 hours to come up with the friction deterioration curve for the aggregate. Now we have a video demonstration on how to prepare the aggregate ring. This is prepared by our PhD student Omole Boyega. Now I'm gonna play that video demonstration, which is about for 20 minutes. And that video will give a visual experience on how to prepare ring, how to do polishing and friction test. I'm going to stop here and going to play the aggregate ring preparation video demonstration.
Good afternoon, everyone. My name is Omole Boyega, and I'm currently a PhD student at the University of Texas at El Paso, and I'm currently working on the TechStuds funded project titled Frictional Characterization of Texas Aggregates. And in the course of this project, I'll be testing about 110 aggregates in Texas. I'll be testing for their friction values. So in this presentation today, I'll be giving an extensive overview on how these aggregate rings are being made and how the three-way polishing device is being run on these aggregate rings. So I'll be showing how the aggregates are being sorted, prepared, washed, how the ring is being made, and also how the three-way polishing device is being run on this aggregate. In this project, we strictly follow the ASHTO PP103 standards, but we made a little adjustment just to suit our research purposes. And there's a justification for every adjustment that was made. So I'll be shaking these aggregates for 5 minutes. After 5 minutes, I'll take out the aggregates retained in the 9.5 opening or 3x8 inch sieve. And the whole idea behind this is to make sure we have as much as 7 pounds, which is also equivalent to 3.5 kilogram retained on the 9.5 opening sieve. Because for us to be able to make one ring, we need at least 3.5 kilograms of the aggregates. This is the amount of aggregates we got retained in the 3/8-inch sieve. And like I said earlier, we need at least 7 pounds, which is approximately 3.5 kilograms of aggregates to make one ring. And from each aggregate source, or each different aggregates, we make 2 rings from each aggregate, then we average the values of the friction for our own friction value. Next step is to wash the aggregates. And the main reason why we wash the aggregates is to remove dust, clays, and fine particles. So I'll be washing the aggregates now. Right now, the water from the aggregates looks colored and dirty. So I keep rinsing these aggregates till the water becomes clear. That's when I know when to stop. So water is clear now, and the washing of our aggregates is done. After washing of our aggregates, the next step is to dry our aggregates in the oven. And according to ASHTO PP103 specifications, the aggregates is to be dried between 230 degrees Fahrenheit and 240 degrees Fahrenheit. In Celsius, this is about 110 degrees Celsius to 115 degrees Celsius. So I'll be drying the aggregate in the oven till the weight becomes constant and the moisture is fully evaporated. This is the process of ring making. And the first thing we do in this process of ring making is the mold preparation. So I'll be walking you through how we prepare our mold and how we make the rings with the molds. Our mold is divided into 2 parts. We have the smaller part of the mold, which is this. What this does is to just prevent our Portland cement from slipping out of the mold when we pour it inside the mold. Then we have the larger part of the mold. This is where the Portland cement and the aggregate sits on. So the first thing we do is to grease our carbon paper. Which is this. And the main reason for greasing this is to allow our ring to demold easily by the time we are done making the ring. That's the main reason we grease this carbon paper, so we don't allow the cement to stick to the mold, which causes difficulty in demolding. So we grease our paper thoroughly before preparing the ring. So we use our grease and petroleum jelly mixed together. This is the grease and petroleum jelly mixed together. After doing this, before we proceed, the first thing we have to do is to change our gloves. We are changing our gloves so the grease doesn't come in contact with the aggregate, and also the grease doesn't come in contact with the surface of the mold. Because if the grease comes in contact with the surface of the mold or comes in contact with the aggregate, there's a high chance this will affect our friction value at 0K, 50K, and 100K. So we try our best possible in the lab to reduce anything that can affect or alter our friction value. So after greasing the hard paper, we replace or change our gloves. After this is done, the next step is to arrange our aggregates inside the mold. And there is a specific way this is done. We don't just randomly dip our hands inside the aggregate and start arranging them in the mold. So there's something we call good aggregates and bad aggregates. I consider this as a bad aggregate, and I consider this as a good aggregate. The reason for this is this aggregate has an angle which allows it to bond properly with the cement, but this aggregate is flat. It has no angular shape, and there is no proper bonding or interaction with the cement. So if we use this along where the wheel path of the three-wheel polishing device goes through, while the three-wheel polishing device is running on the rings, there's a high chance that this aggregate is going to come off, while this aggregate doesn't come off. So we have to carefully select our aggregates and arrange them along the wheel path where the three-wheel polishing device is going to go through. So this aggregate that I consider as the bad aggregate can be arranged on the wall of the mold. This is the bad aggregate. It can be arranged on the wall of the mold like this. While this aggregate with good angularity will be placed along the wheel path. So this, it has a good angularity. This also has a good angularity. The aggregate has been fully arranged inside the mold. After arranging the aggregate inside the mold, we have to fill in the little voids that the aggregate cannot fill. We have to fill in those voids with mortar sand. And this has to be carefully done. It has to be carefully done because if this is the aggregate, the mortar sand cannot fully cover the aggregates. It has to go halfway and not fully cover the aggregate, because if it fully covers the aggregate, there will be no proper bonding between the aggregates and the cement. Once this has been completed, the next step is to mix the cement and water together. After that, we pour it inside the mold. The amount of cement that will be used is 2,400 grams, and the amount of water that will be used is between 220 grams to 240 grams, depending on how workable our cement mix is. I'll be measuring out 2,400 grams of cement. And this is 220 grams of water. In the cement. Now that this has been mixed properly, the cement and the water, the next thing to do now is to pour this inside our mold with already arranged aggregates. Now we pour the cement and water mix inside the mold. So we just pour it around to ensure even distribution. So after this, we leave the cement to set for about 6 hours. After 6 hours, we demold our ring. This is what our ring looks like after demolding. So once we are done demolding our ring, we place our ring inside the sample holder. This is the sample holder. It's part of the three-wheel polishing device. So we place our ring inside the sample holder. Right now, I'm going to give a brief description of the DFT machine, the dynamic friction tester. This is the machine that we use to test and measure our friction values. The DFT has a rotating disc and 3 rubber sliders. The DFT measures the coefficient of friction between the rubber sliders and the contact surface. And the rubber sliders is just a simulation of the tire to road pavement interaction. And I'll also be giving a brief overview of the three-wheel polishing device. The three-wheel polishing device was built according to the AASHTO PP103 standards. And this three-wheel polishing device exerts a total force of about it's usually between 146 pounds to 151 pounds on the sample. DFT, we follow the specifications of ASTM E1911. So we place our DFT on the sample holder. And then we connect our water hose to the DFT because the DFT usually runs under wet condition. Then I connect the DFT to the power supply. Then also I connect the DFT to the power cable. So we have a software that we use to run the DFT. So I'm going to start running the DFT now. So the loud noise you heard was when it got to 80 kilometers per hour, the rotating disc exerted on the aggregate surface and it made that loud noise. Then it decelerated back to 0 kilometers per hour. So usually here in CTIS, we run this test 3 times, then we average it to get our final friction value. So I'll be running it 3 times. The second test has been completed. Now I'll be running the third and the last test. The third test has been completed. After that, we disconnect our hose from the DFT and we disconnect all the cables and get the DFT machine aside. The next thing I'll be doing right now is to dry the surface of our aggregate ring. And the main reason why we do this after running the DFT on the aggregate ring is to maintain consistency and control our polishing conditions. That's why we always dry the aggregate ring after running the DFT. Oh, and one other thing is also to avoid slurry inconsistency. So we do that right after running the DFT on the aggregate ring. And what we use for this is we use a hair dryer to dry our aggregate ring after running the DFT on it. Once we are done with this, we'll slide our sample holder back into the three-way polishing device and run the three-way polishing device for either 50K or 100K, depending on what we are doing. So after that, we run it for another 50K. I hope I've been able to give a very good walkthrough on how we make our rings, how we prepare our rings, how we sort out our aggregates, and how we run the rings in the three-way polishing device, and also how we run the DFT on the rings. If you have any questions, please feel free to ask during the course of this workshop. Thank you, everyone.
All right, so that is about the way that we prepare aggregating and we do polishing and friction test. Since we are running late, I would like to continue without the break. So as part of these results section, so we tried to develop some alternative aggregate friction test. So as I have presented before that the conventional test method as per SOPP 103, it takes like 43 hours and it needs a polishing device and a friction device. So to accelerate the test process, what we did was we looked at like where were the gaps in this sample and where are the opportunities to accelerate this process. So what first we found was like the sample preparation as per SOPP 103. As per this method, the curing time is about 12 hours. Then to accelerate the sample preparation process, we try to use quick setting cement and water as an alternative method for the sample preparation. And the time this method takes is just 5 hours. So instead of 12 hours curing time, using quick setting cement and water, we can just wait for 5 hours for curing the aggregate ring. And the other thing that we did was same as asphalt mixture friction deterioration curve. We tried to uh, accelerate the test process by doing the power fit process by polishing the aggregate rings until 25K polishing cycles. So using the friction values that we get up to 25K polishing cycles, we tried to fit it to a power function and we used that power function to predict the terminal friction value. So in this method, we don't need to polish and do friction test between 25K to 100K polishing cycles. And this method takes 15 hours, whereas a conventional test method takes 43 hours. So there is kind of reduction in the test time and the time for the evaluation of aggregate frictional performance. Then at third, we use the micro dwell method. This is actually used by our Department of Transportation. So here we use cylinders and we subject the aggregates into the cylinder. This is kind of simulates the polishing that happens through the polishing device in the cylinders. And this cylinder runs for 110 minutes plus or minus 5 minutes. Then the aggregates were washed and dried after that and prepared with this kind of aggregating. And here we only get the terminal friction value because we don't polish and we do prepare, so we just get the terminal friction value. This test takes 20 hours. The main thing here is like we don't need three-wheel polishing device. Instead of three-wheel polishing device, we use micro dewell apparatus. As for our study, we found that the R square value of 0.78 between the micro dewell test friction values and the conventional test method friction values. Then at fourth, we tried to come up with some regression equations to predict the aggregate terminal friction value, since we need the terminal friction value in our MLR equation to predict the asphalt mixture terminal friction value. We used Los Angeles test value, microdewell test value, acid insoluble residue test value. The reason why we consider these tests are because Texas Department of Transportation twice in a year conduct these tests as part of the quality control program. So once if we have these test results, we can use these test results as a surrogate to the conventional test method to predict the aggregate terminal friction value. So using these test results, we tried to formulate a MLR equation, and the MLR equation showed an R square value of 0.76. And this method takes 24 hours, and we don't need three-wheel polishing device and DFT device to predict the aggregate terminal friction value using this method. At fifth, we tried to use a powder X-ray diffraction test. Since based on our literature study, we found that aggregate mineralogy controls aggregate frictional performance. We did powder X-ray diffraction for the aggregates, and using the mineralogical composition, we formulated a MLR equation, and that MLR equation showed an R squared value of 0.1881. This is how we do the powder X-ray diffraction test. So once we have the aggregates, we powder them, we place the powdered sample in a mold, and we do the X-ray diffraction test. This test takes just 0.5 hours, and we again no need three-wheel polishing device and DFT device. Then at 6, which is like an interesting test method, We try to use portable extra fluorence analyzer. As per this test method, what we did was we placed aggregates on the PXRF device and we captured the elemental composition, and then we used the elemental composition of the aggregates to formulate a ANN model. And in this ANN model, we predict the aggregate terminal friction value, which is like a output value of the ANN architecture. This method takes 0.5 hours, and again, we don't need three-wheel polishing and DFT device. Among all the alternative test methods, this method gave a good R square value, which is R square value of 0.94. And the other thing is this is a portable device. We can take also to the quarry in order to test the aggregate friction value. Right now, we are in the process of doing some more tests using PXRF device, and I'm gonna elaborate more on the PXRF because our DOT likes this test method. So overall, as we can see here, instead of preparing ring and doing polishing process, which takes 40 hours to get a friction deterioration curve, we directly take aggregates and we capture elemental composition and we input that elemental composition in ANN model, and this method takes 0.5 hours. When we collected the elemental composition for almost like 26 aggregate sources out of 110 sources that we have in the state of Texas, we found Mg, Al, Si, K, Ca, Fe, and Le as the common elements among the all aggregate types. And the ranges we presented here as minimum and maximum that we observed. As we can see, these are the commonly observed and the high percentage elements, elemental composition in the 26 aggregates. Then we tried to verify the repeatability of the PXRF. We selected few aggregates, one aggregate type among the all aggregates. Then the repeatability study showed that the standard deviation is less than 10% for the selected aggregates. Then we modeled this into ANN architecture. One we did was to predict the entire friction deterioration curve, and the other model that we did was just to predict the terminal friction value. Here I am showing for the entire friction deterioration curve, as I previously showed for the terminal friction value, the R square value was 0.94. As you can see in this table, like none of the R square values, whether it's for training or testing data set, are not less than 0.80. And this shows that the R square values are above 0.75 and the model is predicting well the entire friction deterioration curve. Just to illustrate the measured and predicted friction deterioration curve, I selected one aggregate types among the commonly aggregates that we have in the state of Texas. The blue purple ones are the measured friction deterioration curves, which takes 40 hours as per the conventional test methods, which requires ring preparation, polishing, and friction test. The red ones are the predicted using the ANN model, and it takes just 0.5 hours. As we can see for all the aggregate types, the measured and predicted friction deterioration curves are close to each other. This shows that the PXRF can be a alternative and that can be used as a surrogate to the conventional test process. So in summary, if we look at the surrogate test method, if we have a mixed design and if we are trying to prepare a mixed design using a trial mixed design sheet, then if we know the alpha and beta parameters by doing variable feed, and if we know the aggregate friction value, then we can predict the asphalt mixture terminal friction value, that is at 150K polishing cycles. To get the aggregate friction value, we don't need to prepare aggregate ring and do polishing and friction test. We can use PXRF method, and based on the XRF ANN model, we can predict the aggregate terminal friction value. So this method takes just 0.5 hours. We'll go directly from the mixed design sheet to the terminal friction value, whereas a conventional test process that we follow as per ASTO PP 104 takes 50 hours. We have these three publications as part of the aggregate friction research, as I have presented already the two publications that we have. If interested, you can refer to these publication about more details about our research findings. Then let me move on to the conclusion. So the main goal of this research is to incorporate frictional resistance into the current BMD process. Since so far we have focused on improving the structural performance, there is lack of emphasis on incorporating frictional resistance during the mixed design stage. So the first question comes was how to improve the mixture frictional performance. So our findings showed that if we target the intermediate portion of the aggregation, we can improve the mixture frictional performance by using minimum amount of high friction resistance aggregate. The same findings we verified through case studies and field friction studies, and the case studies confirm that aggregate type in the intermediate portion controls the mixture frictional performance. Our field studies also confirm that aggregate type control the mixture frictional performance, and the all remaining mixture parameters effect on the mixture frictional performance is negligible. We tried to develop a accelerated test method and MLR method as surrogate to the conventional test method, which takes almost 50 hours. Both methods showed good R square values. Those can be used to evaluate the test time for determining the mixture frictional performance. We also proposed a combined framework which tries to consider friction, rutting, cracking, and moisture damage performance. Using that approach, a mixture can be made resistance for all the four performances. For the MLR model, we need the aggregate friction value. So instead of using conventional test method, which takes 40 hours approximately, we can use PXRF or other alternative test methods. There is not only one test method like the PXRF, we also have XRD method, a conventional test method, MLR model, and the microdeval ring method. So those can be used as surrogate to ASTO PP103 method. So the near future work that we have been doing as part of this research study was we are trying to construct some test sections for field verification of that intermediate portion on skid resistance. And in the lab, we have been emphasizing on the frictional resistance that is captured using DFT device. And in the field, as we know, we use skid trailer device. We are trying to correlate, even though there are literatures that is showing good correlation, but we are trying to do by our own some field correlations to see how the friction value that is captured using DFT and the skid numbers captured using the skid trailer test correlates. And we are also in the process of validating the portable XRF ANN model for predicting aggregate frictional performance. As I mentioned, we use 26 aggregate sources. We are trying to increase the number and to go until 110 aggregate sources that we have in the state of Texas. And we are trying to develop standards for using three-wheel polishing device for the aggregate and asphalt mixtures frictional performance evaluations. This may help the DOTs for their routine test purposes. And we are also trying to finalize this method to incorporate frictional resistance into the BMD process. Then with this, we would like to acknowledge the Texas Department of Transportation for their funding through the research project ODA 7108 and the interagency contract on aggregate frictional characterization. We would like to specially thank Daily Olivia and Dr. Mustafa Zaman of the Southern Plains Transportation Center for the invitation and opportunity to present our research findings. With this, I would like to thank and I would like to give the mic to Dr. Abdullah.
Hey, Sandeep, good job. There's nothing more to say. I think we're available for questions. Sorry that took longer than we anticipated, but I think you did a great job. You're like 3 minutes before time, but we're here. If you have any questions, we'll be glad to. I know there was tons of information in the workshop, but we're available for questions.
So, Imad, I want to thank you and your group. This is Musharraf Zaman. This is an outstanding and excellent example of a workshop. I particularly like these videos that you have shown. There's a ton of materials that you have covered. I don't know where to start, so I'm not going to ask any technical questions because I have too many. But this is a great example of a workshop. So, Imad, I want to again thank you and Sandeep for a wonderful, wonderful job. So we'll follow up with questions and discussions later on because I think this is an outstanding presentation by any means. A lot of technical content, very significant study. So thank you so much.
Thank you.
All right. Yes, excellent presentation. We do have a couple minutes. If you have a question, please post it in the chat or you can raise your hand. We may have time for 1 or 2 questions. While we're waiting, I do want to remind folks that we will be sending out your professional development hour certificates probably within a week or 2 after this presentation, and we'll have a post online that you can share as well. And we'll also be sending out a survey. So do keep your eyes peeled for that survey to let us know how we did and suggest future topics for other workshops and webinars. So yeah, as we wait for questions, just want to thank Imad. It's a great presentation, Imad and Sandeep. Excellent job. We have about a minute left. Last call for questions before we conclude.
And Michael, this will be also posted on our website, right?
Yes, correct. We have a recording, and with Imad's permission, we'll post that for everyone to share.
Of course, sure. And if anyone would like to work with us, we're in the middle of this. We've been doing a lot of work for other DOTs and especially suppliers that would like to test their aggregates and aggregate sources. We're more than happy to help and support.
So, Imad, I think you open a potential work for you, right? So in Oklahoma, Texas, we're neighboring states. In fact, a lot of aggregates from Oklahoma are used in Texas. So you may want to consider using some of our aggregates, right?
Actually, you guys are some of the sources, right? Texas uses a lot of Oklahoma source aggregates. So yes, we're testing some of your aggregate sources. We're trying to test all of the sources that TxDOT, especially TxDOT uses throughout the state. So
excellent.
All right. Well, thank you again. We've reached our time. If you want, Imad and Sandeep, would you want to post your email addresses in the chat? That way people can reach you if they have questions afterwards.
Sure. If I'll post mine, and Sandeep is in line for a lot of jobs. So if anyone is interested.
Fantastic. Congratulations, Sandeep. That's exciting. I hope you find a wonderful place. I'm sure you will.
Excellent. Thank you.
All right. Thank you so much, everyone. There's email in the chat if you have questions. Look forward to our next event in the near future. Hope everyone has a great rest of your day.
Thank you.
Thank you all. Thank you for your time.